Hi, science friends. I have two quick announcements I wish to make before we get started. First of all, somebody pointed out yesterday that there were some questions about PSI on the assignment. So I apologize for putting those on there when we didn't talk anything about PSI. You will not see any more PSI problems. That's not something that we really do a whole lot with. So if you worked those out on your assignment, great. If you didn't, no big deal. But I did send the conversion factor out in a remind message yesterday, so I hope that you got that. Today we are going, also the second announcement, I was also alerted yesterday, so basically I really failed yesterday, but I was also alerted that maybe you didn't have all of the notes, and so when I got to investigating this, it appears that we had a mishap in the copy room, and that I think I had when I gave them to be copied, they were copied front and back, and so it didn't get the backs. And so you only have the odd pages. So in the stream in Google Classroom, I made an announcement about this. I do really apologize for that. But I posted a PDF of the notes, and so if you were able to print those out, you may want to go in and print the even pages out. I think there's 4 pages that are even. And if you're not, then just kind of follow along in the lesson, and if you want to take a few extra notes on your own paper, then you can do that. Okay, I want to start out today with a bell ringer. I don't usually do these in a lesson, but as I mentioned to you yesterday, this test has a lot of concepts that students don't really get. They get the math, but they don't get the concepts. And so we practice the math in our assignments every day, but I want to use this time to kind of practice the concepts. So let's take a look at this first question. State the standard temperature in kPa, ATMs, and mmHgs. Those are right there on your formula sheet. You've probably already committed them to memory. If you haven't, they're right there in front of you, easy to access and read. But it's 101.3 kPas, 1 ATM, and 760 millimeters mercury are the standard temperature. Not standard temperature, standard pressure. That should read. Standard temperature is 25 degrees Celsius. Okay. How does an increase in temperature affect the kinetic energy of a gas? And so this question, and then the next one too, those are kind of those concepts. I don't want you to really memorize these answers. I want you to think about them conceptually, okay? So remember, temperature is a measure of kinetic energy. We talked about that yesterday. And so if you increase temperature, that is also going to increase because it's a measure of kinetic energy. And so they are directly proportional. Okay. The second one, how does an increase in kinetic energy affect the gas pressure? And so we talked about that a little bit yesterday. I want you to imagine if we had 10 students in my room, and you were walking around in my room. We took out all the furniture, and you were just walking around in my room rather slowly. You didn't have very much kinetic energy. Okay, there's not a lot of pressure. There's not a lot of people bumping into each other if you're walking around slowly, and so the pressure in the room, if you work the gas particles, so to speak, is relatively low. But if we turned up the heat and we turned up your kinetic energy and made you move faster, then you're going to be bumping into each other a lot more. There's going to be a lot more collisions, and thus the gas pressure would increase. So this one should be increase as well. So if you struggled with those and you didn't know the answer before I gave them, take some time to kind of go back and review that content, or just really think about it conceptually. Don't just guess increase or decrease. Have some type of reasoning that you can use to explain it. Okay? So today we are going to talk a little bit about liquids. And so liquids have a special type of forces that gases do not have, and they are called intermolecular forces. So in molecules, we have 2 different types of forces. We have intermolecular forces, and we have intramolecular forces. Okay, so the bonds that we have talked about so far, like the ionic bonds and the covalent bonds, those are an intramolecular force, okay? If we have a water molecule, it's like an H and an O and an H, right? These are covalent bonds. They represent an intramolecular force. It holds one molecule. You may want to write this down in your notes together. If you take AP with me this next year, this will be really important, okay? So those are intramolecular forces or intramolecular bonds, so to say, okay? Now, an intermolecular force is forces between two molecules. Oh, very good, C. Okay, so if I had another water molecule right here, okay, those are still my intra, right there, still my intra. But I also have a force that draws these water molecules together, and that is an intermolecular force. Typically, intermolecular forces are going to be between atoms of opposite charges. So we know oxygen, if you look at it on the periodic table, it typically has a -2 charge. Hydrogen has a +1 charge. And so the hydrogens are going to be attracted to the oxygen, and the oxygen's attracted to the hydrogens. And so when we look at water, like if you spill a glass of water on the table, it puddles, right? You don't have individual tiny little microscopic droplets that are spread out all over the table. It puddles because of these intermolecular forces that kind of suck it all in together, okay? And so that is something that's unique to liquid that gases don't have. Gases are not attracted to one another in the same way that liquids are, okay? This also makes liquids more dense than gases. When we look at, the gases, remember if we had our solid, our liquid, and our gas box that we drew the other day, those gas particles are going to be spread out all over, versus the liquids are going to be a little bit more close together. And because there's more molecules or more atoms, either way you want to look at it, in the same area, that makes this more dense. Remember, density is equal to mass over volume. So this one is technically going to have a lot more mass because there's more dots or particles or atoms or whatever you want to look at in the same volume. I drew these squares roughly the same, right? This one has fewer dots or particles or atoms in the same volume, and so the liquid would be more dense. The gas would be less dense. What about the solid? Where would it go on the scale? Would it be more than the liquid? Would it be between the liquid and the gas in density? Or would it be less dense than the gas? Remember what that solid looks like. All those particles are tightly in nice rows. So you should say that the solid would be the most dense. Okay, more so than the liquid. All right. So that's intermolecular forces. So when particles of a liquid have enough energy to overcome the intermolecular forces between them, then they will evaporate. So when they are able to spread out enough to be able to break down this force, then that will cause them to essentially evaporate, okay, and change into that gas stage. All right. So this process, the conversion from a liquid to a gas, is called vapor pressure. It's called vaporization. Vapor pressure is the force due to the gas above the liquid. So there is a force sitting on top of the liquid from the gas, and that is called a vapor pressure. Now that's only in a closed container, and it doesn't really affect the volume of the thing. I'm not so concerned that you know that much about vapor pressure, quite honestly. So The process of vaporization is called evaporation. You should be very familiar with that term. And it's a cooling process. When things evaporate, it causes it to cool. Okay? When you sweat and the sweat evaporates off of the back of your neck, it leaves a cooling sensation behind on your neck. It's called evaporative cooling. When heat evaporates off the top of the water, like in the summer on the lake, it cools that top surface of the water. It's evaporative cooling. So the hottest particles are going, with the ones with the most kinetic energy, are going to evaporate first, leaving the coolest particles with the least kinetic energy behind in the evaporative cooling process. Okay? So liquids also have a boiling point, and that is the point that they change from a liquid to begin to change from a liquid to a gas. As we mentioned yesterday, this is going to sometimes change at different altitudes. Depending on where you are, it may be a little bit above 212 degrees Fahrenheit or 100 degrees Celsius to boil water due to the altitude because of the pressure. Okay, so boiling point increases at higher pressures and decreases at lower pressures. So if you went and you lived up in the mountains, then it would require your water to get higher than 100 degrees Celsius to make it boil. Okay, and so that's kind of interesting. If you lived in a lower area, then it would not take as much heat to get your water to boil. So at boiling point, the vapor pressure is equal to the external pressure. That's when those pressures are equalized. Okay, so solids are dense. As we said a moment ago, they are the most dense of the three states of matter. And like we mentioned yesterday, all particles are moving, but solids are not moving as much, just because they can't really move around when they're all packed in tight like we drew them in that diagram. They kind of just have more of a slight vibration. These liquid particles, and particularly these gas particles, can move around a lot more. The liquids kind of slide past one another. The gases just bounce off erratically. But the solids have more of just a vibrating pattern in a pretty fixed position. Okay? Melting point. You should be very familiar with melting point, the temperature at which a solid turns to a liquid. So at the melting point, the vibrations are strong enough to cause the particles to break down. So as you continue to heat a solid, remember, if you're increasing temperature, you're increasing kinetic energy. Okay? And so those molecules are starting to vibrate faster and faster and faster and stronger and stronger and stronger. And eventually, it's kind of like an earthquake, right? Like we can have a small little vibration in an earthquake and nothing's going to happen. But at some point, it's going to lose structure and it's going to kind of escape that fixed solid pattern. And in this case, it's going to cause the organization to break down and to move in that next state of matter, which is the liquid. Okay. Now, on the opposite, when you have freezing, that's when the movement, remember, temperature, when you lower temperature, you're lowering kinetic energy. So those particles are starting to slow down. And so as you near freezing, those molecules, now they haven't stopped moving. They don't stop moving until they get to absolute zero, like we talked about yesterday. But they get slow enough that they start to pack together, right? And they get in that uniform solid position, as we've talked about, because they slow down, okay? And so that's going to be between a liquid and a solid. So when we look at solids, solids form a crystalline structure. So they have a very specific 3D pattern, the arrangement of the particles. And if we were in the classroom, we would kind of look at these underneath a microscope. It's interesting to see, and that seems like kind of a biology thing to do, but you can see the difference in kind of, you don't see the atoms, of course, but kind of structural differences between like a salt particle and a sugar particle, because they have those different crystal structures there. Ionic compounds generally have a higher melting point than covalent compounds. That's important, okay? They have a higher melting point than covalent compounds. Some elements don't melt until they're like 1300 degrees Fahrenheit. Like it just takes an enormous amount of heat to melt it. I think salt is one of those. You can dissolve salt, but it takes like over 1,000 degrees to truly like melt salt because it's an ionic compound and it has a very high melting point. Okay. Sublimation, we talked about that in a previous unit in matter. Sublimation is change from a solid straight to a vapor or a gas without going through the liquid phase. We don't, you maybe have ever witnessed this in your freezer. So if you make ice cubes, whether you make them in a tray or you have an automatic ice maker in your freezer, if you leave those ice cubes in the freezer for a long time, you will notice that the ice cubes start to shrink. And that's because of a sublimation. The freezer door didn't get left open. They didn't melt. They sublimated straight from a solid to a gas without moving through the liquid stage in between. Okay? So what we're really going to focus on today is phase diagrams. And we're going to do several of these to practice. You have a worksheet today where you have a front and a back that you are going to do with phase diagrams. Last year, students seemed to have a hard time with these. I'm not really sure why. But all phase diagrams are going to have this same basic structure. Now, where the lines are may look a little bit different. Here we have a line here, and we have a line here, right? But it may be in a different spot. But it may be like that. But ultimately, you're going to have a line that divides this graph or this diagram into 3 parts. And it's always going to be in the order solid, liquid, gas. Solid's always going to be the first one on the left. Liquid's always going to be in the middle. And then gas is always going to be on the right and towards the bottom. Okay? Always, 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 that's how it's going to be. And so when we look at a phase diagram, you have a couple of points that are really important. So first is the triple point. That's where these two lines come together, is the triple point. And so the triple point is where all 3 phases can exist at the same temperature and the same pressure. So on our axes for the phase diagram, on the x-axis, you have temperature, which is usually in Celsius. And then on the y-axis, you have pressure, which may be in ATMs or something else. But the triple point is the temperature and pressure where you can actually have a state of matter in a solid, a liquid, and a gas. Okay? They can coexist at the same time, or tri-exist. I don't know how you would say that. All right? Another important point that you have is up here, usually at the top right of the graph, and it's called the critical point. And it is when 2 phases become indistinguishable from one another. And the 2 phases that it's talking about is always going to be between the liquids and the gases, because that's the 2 phases that are meeting here. Okay? Solids are all the way over here. It doesn't have anything to do with solids. But these become indistinguishable from one another, meaning it's where a liquid changes to a gas, but you can't really say for sure that it's a liquid or a gas. They're essentially one and the same. They're indistinguishable from one another. Okay? Now, to be able to read a phase diagram, you have to understand the changes in states of matter. So we talked about those in Unit 2, okay, when we talked about matter. When you go from a solid to a liquid, that point there is the freezing point, right, or the melting point, depending on which way you're going. If you're going from solid to liquid, it would be a melting point. If you're going from liquid to solid, it would be a freezing point, okay? Between a liquid and a gas is going to be a boiling point. That's what it is called when a liquid changes to a gas. That is boiling, okay? Now down here, Where a solid's going to a gas, that's called sublimation, okay? And that's important as well, all right? And so you need to know these terms to be able to read a phase diagram, all right? So I want you all to take a stab at those phase diagrams that I gave you today. If you need help, reach out to me. Please reach out to me. I expect that my email will be hopping tomorrow, okay? I just don't have a whole lot of examples to go through with you. I want to use the examples for you to practice. They're hard for me to find problems to actually give you to do with them. So see what you can do with those phase diagrams. If you want me to check them before you submit them, send them over my way. I'm happy to do that. Text me, email me, send me a picture of it. I'll tell you if you're on track or if you're not, and I'll help you along with those. Let me know if you have any questions on them. And if not, then I will see you back tomorrow. We'll jump back into a little bit more mathy stuff tomorrow. Y'all have a good day.